And welcome to Chapter 10, Chemical Quantities. In this chapter, we're going to be dealing with just that. How do we measure the quantity of different materials? We're going to be talking about how we count the number of particles, how we estimate the mass of a certain amount of material, how do we calculate the volumes of gases, and finally we'll be talking about how do we analyze the composition of various compounds. Here in 10.1, we're going to introduce you to the idea of what's called the mole. The mole is one of the fundamental concepts of chemistry that you need to understand. We'll be using moles this entire trimester, and so this is one of the key ideas. If you don't understand how the mole works or what the mole is, you need to make sure you're getting help on this right away. If you don't get the mole, it's going to be very difficult to understand the rest of the trimester. Okay, so let's go ahead and take some time to explain what the mole is, if this is this important of a topic. First of all, if we take a look at a balanced equation, what does this balanced equation tell us? Well, in the case of the Haber process, which produces ammonia from nitrogen gas and hydrogen gas, the balanced equation tells us one molecule of nitrogen is going to react with 3 molecules of hydrogen to produce 2 molecules of ammonia. That's what the coefficients tell you. In the previous section, we took a look at how to balance equations. So you can have 1 molecule plus 3 molecules producing the 3 molecules of the ammonia, or you could multiply that by 10 and say 10 molecules plus 30 molecules of hydrogen will produce 20 molecules of ammonia. Or you could do them in dozens, or hundreds, or thousands, or whatever the case may be. It's always going to be in a 1 to 3 to 2 ratio, at least when you're dealing with this particular reaction. Now, how many molecules are we actually talking about reacting? Well, think about this. If you have a 2-liter pop bottle filled with nitrogen gas, all right, this is the number of particles that we're talking about. 5, 5, with 21 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So if you put the commas in, there's a comma there, etc. So you have millions, billions, trillions, quadrillions, pentillions, hexillions, if that's really the term that you use. That many molecules of nitrogen gas are in a 2-liter pop bottle. So we're dealing with huge numbers of particles, and that's just in a small pop bottle. What about when you're dealing with things in the atmosphere? What about when you're doing things on the industrial scale? Obviously, we're dealing with tremendously large numbers. Okay? Now, because we're dealing with tremendously large numbers, we should reintroduce you to the idea of scientific notation. The way you write things in scientific notation is to simply put a decimal after the first non-zero number. So we'll put the decimal between the 2 5s, and then express it as a power of 10, the power telling you how many spaces you're going to move the decimal. So if I put the decimal here, and let me change colors so we can kind of keep this different. If I put the decimal here, and the decimal really belongs all the way down there, I'm going to have to move it 22 times to get it to there. So I'm going to use the power of 22 to explain how many places we're going to move that decimal. So this in scientific notation would read 5.5 times 10 to the 22nd molecules of nitrogen. Alright? So that's something that we should review. If you're not quite sure how to use scientific notation, that is something that you'll want to ask me about. Alright? Now, how can we count that many particles? Well, in reality, you may already have some experience with this. When you're dealing with buying things in bulk, say if you go to Meijer's or Kmart or Walmart or something like that, and you're going to buy some bulk candy, you put a scoop, you take a scoop, put it in the bag, and you bring it up to the register. Well, how do they know how many pieces of candy that you put in the bag? They weigh it. So we actually count by weighing. And when you get an accurate mass, you use a conversion to change from the mass to the number of particles, or from the mass to the number of pieces of candy, or if you're going to the hardware store, from the mass to how many nails that you want to buy, or whatever the case may be. Now, example number 1 and example number 2 are two examples that we do need to tackle in class. We're going to talk about how we can count the number of grains of sand in a beaker, and we're also going to give you a sample of aluminum, and we're going to calculate the number of atoms in there. So just let me put a bracket around this, and this is going to be in class. We'll take a look at that. But clearly we're dealing with astronomically large numbers, as we showed from the 2-liter pop bottle of nitrogen. So because of that, we have to have a way to more effectively deal with these large numbers. So we've come up with a system that will express these large numbers. Now, just to kind of lead up to this, let me show you how this works. We have terms that mean certain types of numbers. For example, if we say the term couple, we know that we're meaning 2. If you buy a couple of tickets, you buy 2 tickets. We know that 1 dozen equals the number 12. You can have a dozen donuts, a dozen cookies, a dozen muffins, a dozen anything, a dozen kids, a dozen people, whatever the case may be. So 1 dozen means 12 of anything. The term ream refers to 500. All right? That 500 is typically used with paper. So when you open up a package of computer paper, it comes in 500 sheets. That's 1 ream. But you don't have to have a ream of paper. You could have a ream of anything. Well, in chemistry, we use the concept of the mole. The mole is also a number, and it's the number that's equal to 6.022 times 10 to the 23rd. Now, you can have a mole of donuts, a mole of marbles, a mole of anything. Typically, we're dealing with moles of particles. But just so you know, just to kind of put this into perspective, if you had 1 mole of marbles, and there's lots of different examples that you can use. 1 mole of marbles would fill the entire Earth to a depth of 50 miles. So it's an incredibly huge number. 1 mole of marbles covers the entire Earth to a depth of 50 miles. Amazing. Another way that you can look at this, if you had 1 mole of seconds, okay, 1 mole of seconds would be actually, I'm going to say equal to, but it's more than 4 million times the age of the Earth. In seconds. Now realize that the Earth is roughly 4.2 billion years old. So if you convert that 4.2 billion years into seconds, and then multiply that by 4 million, you're still not up to a mole. So this is an incredibly large number. All right? In the next set of podcasts, we're going to start looking at how we can change between moles and the numbers of particles. All right, we'll see you next time.